Uh, we'll get started with the session. Uh, thank you for showing up. Right, we have Ananya today who's going to talk about supervised learning and more specifically linear regression, and then we'll look at implementation of it as well.
Okay. So, hi everybody. My name is Ananya, and I'm currently a senior majoring in computer science at ASU. So, welcome to this session 3 of supervised learning. So, we'll get started with linear regression. And I just wanted to give a quick recap of math session that we did last week. These are the three pillars of math. First one is linear algebra, calculus, and the third one is probability and statistics. So basically, we use linear algebra especially for vectors and matrices. So imagine our data is in the tabular form, like all the numbers are in the table, and we need to represent these in type of matrix or a vector, right? So that's where linear algebra comes into action. So it basically, for example, let's just take the equation of theta is equals to x transpose multiplied by x and inverse of it multiplied by x transpose and y. So is written in matrix form, right? So it's just that we need to represent this data in matrix form or a vector form. So that's where this linear algebra will come into action. And about calculus, so just remember that calculus is derivative, and that is uh, like rate of change. So basically, rate of change is nothing but when we talk about gradient descent, which we'll be talking in the later slides. So it's just while calculating gradient descent, we'll be calculating it using calculus. So we use derivatives to update our parameters step by step. So we'll get the final answer using calculus. So that's why calculus is important. And regarding probability and statistics, we'll be calculating mean and variance. So variance is nothing but how scattered our data set is. It represents that, and mean it's just the average. So, and we will also be calculating cost functions like MSE and MAE, and we will get into it deeper later in the session. So just remember that linear algebra, calculus, probability, and statistics are just like building blocks to get started with ML. So yeah, this is about math recap. Do you have any questions? Okay. Let's get started with supervised learning. So, what is supervised learning? I'll give you an example first, and I will let you know the definition later. So, let's just understand it visually first. So, we have a cat and we have a dog. So on internet we have like loads of pictures of cats and dogs, and in Pinterest also we'll find n number of pictures of these cute pet animals. So how do we feed the data to the AI model so that it learns that this is cat or this is dog? Let's just see how it works. So let's assume that input label X. X is nothing but cat or a dog. We That is our input label, and output label is Y. So basically, feeding input to AI model so that it predicts output, whether it determines if it's a cat or a dog. So basically, we are giving label data to the AI model so that it knows that it can differentiate that this is cat and this is dog. And basically X and Y. We'll feed X and Y together to the AI model so that it learns that this is cat and this is dog. Along with feeding the pictures of cat and dogs, we are also specifying that we are letting the AI model know that this is the label, like cat picture is this and dog picture is this, so that it learns and it maps X to Y. So, it maps inputs to outputs so that it can predict accurately that this is cat or this is dog. So basically, it can also differentiate by, looking at the features, like cat has grayish kind of eyes, but whereas dogs has like brown or black eyes. So it learns from it. It learns from the data. It sees it and learns from it and labels based on the output. So this is basically the training phase. The training phase is nothing but you feed X and Y, that is input and output labels to the AI. It learns and it maps input X to input, output Y. So that's how it maps. And this is the inference phase. Inference phase is nothing but the final like AI model. Like when you give an input, for example, I give a picture of cat and ask, what kind of animal is this? It directly outputs that this is a cat because it has already learned from the previous data we fed to it. So based on that, it just tells that this is a cat. Do you have any questions? Symbols in the sense X and Y?
It just goes together to the model base. It doesn't have any special meaning
Yeah.
or anything. It's just a representation. That's all.
Yeah, it's just visually representing the.
Just saying X is the input data and Y is the output label that we have, and both of them are used to train the model.
Yeah. So, yeah. Do you have any other questions? So since we visually saw what supervised learning is doing, let's just understand the definition of supervised learning. So supervised learning is a machine learning technique that uses human labeled input and output data sets to train artificial intelligence models. So that means for every input we provide, like an image or a number, we also give the output label so that it knows that they have given an image, they have given a number. So that's how it works. And the model then studies both the inputs and outputs and then maps everything. Like whenever you give an input, it just gives you an answer of output. So that's how it works. And the second statement says that the trained model learns the underlying relationships between inputs and outputs, enabling it to predict correct outputs based on new unlabeled real world input data. So as I mentioned, whenever we feed the data into the AI model, it learns and it predicts. And we also give the output as well to the AI model so that it can predict very accurately later when we ask any questions to the AI model. So in short, just supervised learning means learning from examples where we already know the answer and also trying to make predictions of new unseen data. So that's how it works. And any questions so far? Okay, so that's the definition of supervised learning. Now let's get into the part where supervised learning divides, like it has two categories. First one is regression and the second one is classification. When it comes to regression, it's like continuous values, like it gives a constant number. It predicts a number, like it gives you continuous values. When it comes to classification, it categorizes your answer. For example, you know, if an AI model is trained and we are asked like if this email is spam or not, it predicts whether it's spam or not. That is called category. So basically binary, 1, 0, yes or no. So that's how it works. Whereas regression is a number. It predicts a number for us. It's continuous. Let's understand this by a visual. So again, I told regression is something which predicts continuous values. For example, predicting house price. When you give, like, for instance, number of rooms in a house, so it predicts a price based on the number of rooms in that area or anything. So that's how regression works. Whereas classification classifies whether a particular email is spam or not. So that's how it works. And in the right side, you can see that it says, what is the temperature going to be tomorrow? So it predicts that it's 84 degrees. So that's how regression works. So it's basically giving you a number, like giving you a number as output, and that's how it works. And whereas classification just tells you if it's hot or cold. If you ask like, will it be cold or hot tomorrow? It just predicts cold. So that's how it works. Number, and this is a category. Good. Any questions? All right. So this is about regression and classification. So let's get into the main part of this session, that is linear regression. What is linear regression? So let's understand linear regression by dividing it into parts and understanding each and every word. For instance, like linear. What is linear? It's just a straight line or a straight plane or a cube, etc. So it's a very simple word, right? Regression. So regression is nothing but a statistical method that analyzes the relationship between output and one or more two inputs. So basically, output is the dependent variable and input is the independent variables. So based on these independent variables, output will be generated. That is the dependent one, which depends on number of inputs we give to the model. So, and this AI model will predict a continuous value like a number. And as far as classification is concerned, we'll be doing that in next sessions. So just stay tuned for that. We'll just continue with linear regression for now. Now let's visualize what is linear regression. Let's just take house price prediction problem. Now, in the x-axis, I have area of the house in square feet. And for y-axis, I have price of the house in dollars. So, and these are all real data points, like it has been derived from the real data set. So based on the area of the house, we plot the price of that particular house. That's how this graph works, okay? And now you see this blue line. This blue line is the best fit line. It's called best fit line. So this is how linear regression works. This is basically the predicted line. The AI models predicts a linear line so that it accurately predicts price of the house. Maybe, for example, we'll ask like, what is the price of the house if it's 2000 square feet? And we can just go and refer to the point where, can you see the red mark right there? So just assume that's the 2000 square feet point right there. And we can see on the y-axis what is the price of that particular house. That's how it works. And this is just remember that blue line is the best fit line, and we'll get into much detail later in the slides. What is the?
What's the best fit line?
So it's
Okay.
basically representing what could be the best value if you didn't know the price. Let's say if you didn't know that that red triangle over there is, let's say you construct a new house that's 2000 square feet and in a particular area, and then you want to figure out what is the median price that's going around, right? So you could use this model to say that, okay, my house is 2000 square feet, then the price of it could be this based on the model that we have, because we might not have access to all the data that is there. So that is what the blue line is representing this.
Any more questions? All right.
Yeah.
There is a little deviation of the line, the other point line. So a range would be a better answer for the branch.
Yeah, but that is a much more complicated model architecture. This is like, since we're getting started, we're looking at linear regression, which is one of the easiest models to understand the entire aspect of machine learning. But what you're saying is usually we can look at the range, but for now we just look at. And this like the deviation that you're seeing might occur even in real world, right? Like let's say you're trying to sell a house, and if it costs like 300,000 versus they might kind of negotiate, and then you might bring it down to 275,000. So those kind of deviations tend to happen in real world as well. So it is just a representative value that you can use as a base and then model your price around that. So it's just giving you a metric there. Does that answer your question?
Now, let's learn about the goals, like why are we doing linear regression? Why are we using linear regression for predicting values? So, linear regression is nothing but finding the best fit line and predicting our outputs based on the input. So, our goal is to minimize the difference between actual and predicted values. As you saw in the last representation, pink dots represent the actual data points, whereas the blue line represents the predicted line, right? So we are actually measuring the distance between the predicted point and the actual point. The less it is, the more AI model is working really good. So that's how it works. We'll get into more deeper discussion about it, but just remember that we need to minimize the difference between actual values and predicted values. Again, it just says linear regression is a method that finds the best fitting straight line through data points to predict outcomes. All right. So now we'll be understanding the linear regression again visually. Let's just take area of the house in square feet as x-axis and y-axis as price of the house in dollars. So these are the data points, the actual data point. And yeah, it's the same thing that I told. And this is the best fit line. So our main goal is that we need to find a best fit line which is passing through all the data points, like which actually minimizes the distance between the blue predicted output and the actual, the value. So that's our main motive is. I'm just showing this visually so that you can understand it, and we can go further in the into the next slides. So any questions?
I just want to add a few things here. So the best fit line is not the line that you'll always get, right? So you need to figure out what exactly is the best fit line. So what we start with might not be the blue line that you're seeing over there. That might not be the positioner. So what we are going to look at is how can we train this line in such a way that it can go to this best fit position, right? That is where the entire machine learning kind of lies in.
So how are we going to train the model? We'll see it visually. Again, x-axis area of the house in square feet, and y-axis price of the house in dollars. So these are our data points, all the pink dots. Okay, so let's assume this is the best fit line that our AI model predicted first. As Kaustubh said, there are multiple best fit lines, like this won't be the last one. AI model gradually takes small steps to predict the best one, so that it can predict the actual with accuracy. So let's see the visual representation between distance between the actual points and also the predicted ones.
So what's happening here is basically, let's say, what is a line, right? It's just a mathematical equation. How do we know what is the best fit line? We don't. We start with some random values for this line representation. And then what we do is we basically compute the distance from the data points to the line that we have currently initialized. And then we compute that distance. And then we add up all the distance, right, to figure out if the distance between the actual data points, which is the dots over there, and the line, is it very large or is it small, right? How do we go to the best fit line is what the next representation shows.
Yeah. As you can see, the difference, like the distance is very large here. For the next visual, you see that it turns yellow, and you can see that it is more the distance between the data points and the predicted line is much more smaller compared to the last one. So that's how AI model slowly, gradually takes small steps to reach that position of minimizing the error between the 2 points. Let's see it visually again. So the blue lines right there shows us the minimized errors between the actual and predicted line. So yeah, do you have a question?
What? Can you be a bit louder, please?
Would it also work in like an XYZ plane? Would it work on that too?
Yeah, it does. Right now, we just have one X value, which is the area of the house, and we can have 100 values as well.
Yeah.
So we'll look at how exactly that works once we figure out how it works in two-dimensional space.
Yeah, so for now we just took one input, right? So later we'll be seeing with multiple inputs. So let's just wait for that part. Any more questions? Okay. So we'll be representing the linear regression model now. So this is our graph I have showed you before. Now we'll be showing you the equation of the linear regression model. So for now, so this is a straight line formula, basically mx plus c. So y is equals to mx plus c. That is exactly the same, wx plus p, where x is the input data. For example, here it's the area of the square feet, like the whole area, and w is the weight parameter, like it's the slope that we'll be calculating, and b, the bias, is the y-intercept. So there you can see right there in the y-axis. So that's how we got into this equation. It's basically the straight line equation, y is equals to mx plus c. So now our goal is that when we calculate this y hat, so y hat is nothing but the predicted value, we need to make sure that it is as much as similar to the actual value. Since we need to reduce the error between them, we need both actual and predicted value to be the same. So not same, but at least be similar. So that is our main goal for the linear regression. So this is the equation for it. Do you have any questions? All right. Let's get into the next part. Yeah.
So W is just the slope of the line, right? And V is basically the y-intercept. Because we are training them using machine learning, right? These are the two values that we are trying to figure out. If you remember the animation where the line moved from one position to the other, basically the slope of the line changed as well as the y-intercept changed. Do you know what y-intercept is? Yeah. Okay. So basically, these are the two values that we're trying to figure out based on how far the line is from the actual points, right? So that is what we are trying to figure out. The reason why we call these as parameters is because these are the values that we are trying to figure out using the entire machine learning process, right? So how do we figure out all of this is using a mathematical representation called loss function. I think that is what she was going to talk about. Does that answer your question? Any other question?
So coming to loss function, what is a loss function? Now we all saw the visual representation of the graphs, like we saw the best fit line. It was one was near x-axis, which was very far from the actual data points, and one the yellow line we saw was really near to the data points, right? So how exactly we know that whether this is the best fit line, I mean, this line is good or bad to that particular data set or to that particular data points we have plotted in the graph. So that's where loss function helps you. So it's nothing but measuring how far your predictions are from the actual values. So based on this calculation, we can determine whether this is the best fit line or not. So the distance is a representation of how far our values are. As you saw in the visual representation that we have determined it by using a line. So that's the distance. Basically, we call that as error. We'll get into it more in detail. So one way to calculate this loss function to determine whether that line is good or bad is using mean squared distance. So basically in mean squared distance, we subtract actual value with predicted value. So yi minus y hat, and we'll be squaring that so that we don't cancel the negatives and positives, and we'll be summating all the stuff we have n number of data points, right? So we'll be doing it for every n, and we'll be dividing it by n. So that's how this equation came. L is equals to 1 divided by n, summating it with yi minus yi hat whole square.
Did everyone get what I is? Yeah.
So that's how loss function works. This is called mean squared error. So basically we are calculating the error, right? Distance between the actual and predicted value.
The reason why it is called error is because we want to minimize the distance, right? This distance is called error in ML terms.
Yeah. So
yeah.
Yeah.
Sorry? Oh, it's just a scaling factor, mathematical scaling factor. Even if you don't have it, it'll still work.
Yeah. Go ahead.
Does that record?
Yeah. So the end is the number of samples.
Yeah.
Yeah.
So basically, you're trying to figure out like.
If sample increases, the loss will decrease. One by.
It basically stays in the same scale. Like, let's say you have 100 points now. You divide it by 100, the scale would be the same of the loss. Let's say you increase it to 200 points, the values, the loss value that you would get again after that computation would also still be the same scale. Like, that's the reason why we do that. There is no other significance to doing that scale. Yeah, one second. Someone had a question in the back.
Oh. So what is the end sigma I at this point?
So I is basically, you remember all the pinpoints that we had, like the each data point, right? I represents all those values. So let's say we have 100 points there, n would be 100. So we go from the first point till the 100th point. And then we compute the distance of what exactly that y value is, the price for each house whose area is some particular value. And we subtract it with the predicted output for each line. So what you can think of is that so if you just look at what is happening over here is that this is the y value, right? But let's say y hat would be this value for this particular point. Right? We're basically finding the difference between them, squaring it up.
Why is the point of y hat is the error?
Y hat is the predicted value. Y is the actual price. Y hat is the predicted price. Yeah, y hat is the line. So once you have this line, you can fit that area into this equation, and then you can get the y value, y hat value, right? This is nothing but y hat. Yeah. Any other question?
So yeah. Now let's get into gradient descent. So now we know by calculating loss function, we know whether it's a best fit line or not. Now, how exactly are we going to find this particular, error or something? Wait, let me just show you a visual representation before starting it. So the question is, how do we exactly reduce this loss between actual and predicted value, right? That's how gradient descent helps us. For example, let's just consider this is the A mountain, and you are on top of the A mountain. Sparky is representing you, right? So you can't like jump and reach the bottom in one go, right? You eventually have to take small steps. You have to, take small steps through that slope, and you have to get to the bottom very slowly, right? So that's what gradient descent is. Let's see the visual representation now. So Sparky is taking small steps to reach that lower point of the mountain. So that's what AI models does as well. So it takes small steps to reach that, to minimize that error between the actual and predicted value. So that's what it says visually here. Any questions?
So basically what's happening here is that if you remember the animation where the blue line went from blue to yellow, it didn't directly jump from blue to yellow, right? So there was a gradual change where it moved from that position to the yellow line position. So that is what this is representing. So when it was at the initial blue line position, which was down below, right? The error was very high. So that is what it is representing. When this error is pretty high, then the gradient is high. Once the model is trained, the gradient would be pretty low. That is what we are trying to achieve over here. Yeah. Any questions on that? All right. So yeah. Okay, go ahead.
So gradient descent is just that we adjust the weights a little. So at a time, moving downhill, and until our model is accurate and is predicting very near to the actual values. So it's just a fancy representation by saying gradient descent. So yeah, and we'll be seeing the function of this. Now let's take our x-axis as steps and y as loss value. And this is the slope maybe. And now you see a ball right there. So we'll see a visual representation first. As you saw, the small orange ball was at the top, and it was taking small steps to reach the very bottom of it. So that's what minimizing the error means. So it gradually took small steps to reach that point, that lowest point. So that's how gradient descent works in AI models as well.
Yeah. Yes.
Exactly. It iteratively checks, like it checks the gradient descent step by step, and it gradually comes to that small point, that small error.
So yeah, just to add to that, it checks that value, updates the W and B values in the equation, and then again computes what is the actual output, and then again compares the distance between the Y and the Y hat for the next step, and then again it basically repeats that process. Yeah. Yeah.
So the example where it's just a straight line, are you saying that gradient descent in the line would essentially oscillate amongst the data points until it settles?
Exactly.
So my question is, why did you need to do that when you could just already know the distances from like the points to the x-axis, something like that, and then just immediately drop the middle?
Can you repeat that?
Yeah, so like, wouldn't it already know like where these data points are and their distances? So like, why would it need to bounce around rather than just immediately finding this point?
So how do you know that midpoint? First question.
Because aren't these data points all relative to one of the axes? So it's like we already know where the data point is relative to, either the x or y axis.
Not necessarily, right? It could be anywhere on the plane. So if we go back to that, let's say this is the data distribution that you're seeing over here. For one sample, which is over here, right? The value of the price of the house is here. But let's say you go above, the same area, like a house that has the same area has a different price. So how do you know that this is the relationship between X and Y? There is no definitive relationship. If there was a definitive relationship between these two values, obviously you could just draw this line in one go. Because you don't have a definitive relationship between the values that are the actual values, you can't really average it out and then say that, okay, this is the final value. Does that answer your question?
Got it, yeah.
Oh, we can discuss more as well. after.
Okay, so what about?
Yeah. You can answer if you want to.
There was a problem. Could just ask this how to go a bit for line and a bit for play. Yeah. So the thing is that with the midpoint, you're taking the midpoint of the entire. So I imagine if there was a point that's skewed. So imagine a point that was below the y. Okay. That skewed the plane. How do you identify that that's the local? How do you provide your that just takes the midpoint of the entire. Did you take into account the outliers and the factors, the fact that there's a spread between the area of the those kind of spreads start to cut down those deterministic patterns and just like take a midpoint. That's why we have to implement machine learning algorithms that take into account all of the points and the relationship. Does that help? Yeah, that's what it's like.
Can you be a bit louder?
So ways that outliers like usually beta like we just not data here that is not part of the data start developing the outlier you get the number of outliers significantly less than the data distribution like that.
Can you ask the question here, please? Can you ask it louder?
But we say that in the data preparation, we take out some of the outliers which are very far away from the point every other time. But then if we take out the outliers, then we come back to the question, can change it. And then consider the outlier, then the graph changes. I agree with you, just smaller slope, but it does change.
Yeah. So there is no question of taking out the outliers, first of all, right? Because let's say if you have 1,000 data points, you want to use all the 1,000 data points to figure out what is the best representation of that value. The reason what he was saying was, can we directly find the line without doing any kind of training? Yeah. That is where a lot of, we can consider that there is no problem with that, because let's say we have a outlier over here, because it's just one value, there might be a little bit of deviation on the line. The slope might change a little bit, but it doesn't majorly affect it. Because the values of the predicted values cannot be, the loss between the actual values and the predicted values can never be zero. In this scenario, it's totally fine to have a little bit of change. Does that answer your question? Anyone else has a question? Okay.
So, as per the equation, for the gradient descent, we'll be representing it by W. W is equals to W minus alpha. Alpha is nothing but learning rate. So basically, learning rate is a value which tells how much of a small step that you need to take to go to the next point, and we'll be multiplying it with the derivative of loss function. So basically, alpha is nothing but you're on a mountain and you are going down the slope. So basically, the amount of step you're going to take to the next to reach the next step. That's what alpha is. Is that clear? Because we'll be deriving an equation using alpha, so I just want to make sure that you guys understood what alpha is. All right. So now let's get into math. Now, for the equation setup, we'll be taking the line equation. Y hat is equals to Wx plus b, which is the equation of the line. And the loss function, which is 1 divided by n, summation of actual values minus the predicted values, whole square. And we'll take the gradient descent equation as well, which is W is equals to W minus learning rate, which is alpha, and the derivative. Now here's where we compute the back propagation. Now, we are just taking the loss function and we are substituting the line equation into that particular equation. Now, we can see that delta L divided by delta W is equal to delta divided by delta W into multiplied by 1 divided by n summation of yi minus the line of equation. It's nothing but just the predicted value. So as you can see in the equation setup, we had y hat is equals to wx plus b, right? So we are just substituting that instead of the y hat in this equation.
So what exactly we are trying to do over here is that if you remember the previous plot where a ball was kind of rolling down the hill, we are trying to find out what is the change that we need to do to the values of W and B with respect to the loss, because that is what we want to minimize, right? So how do we minimize if the slope of the line on the loss curve becomes 0? That is when we can say that we have reached the best W and B values, right? That is what we are trying to do over here. And to do that, we are taking small steps. That is where the gradient descent equation comes into picture.
And now the final equation becomes delta L divided by delta W is equals to 1 divided by n summation of minus xi after calculating the whole derivation, and we'll get that specific equation. So it's basically for your clarity, I just want to tell you something like at every step it takes, the models looks at the previous step and learns from it, and it predicts like how wrong it is, so that it can take the next step more small and can reach the bottom, slowly. So and then this is how back propagation works. If instead of equations, I can give you an example. So let's imagine you are playing, you have arrows and you are trying to hit the bullseye. So every time you throw the arrow, it will go somewhere else. It can go on some other part of the board, or it can fall down as well. So if you observe for each throw, you can calculate the distance between the bullseye and the distance between the one you threw the arrow and it fell on that particular area. After measuring this distance, you can position your arm in such a way that you can hit the bullseye and it straight goes to the bullseye. That's how gradient descent works. It positions itself in such a way that it can reach the lowest point or the bullseye that we use throwing using an arrow. So that's how it works. Does that help?
Any questions on this? Oh, it is just the derivative of our equation. So if you do the dou by dou W of the entire loss equation, you get this following equation. That's it. Because it's just a chain rule. If you remember the derivative math, if it is n squared, it becomes 2n, right?
2n, yeah.
I think 2 is missing over here. But whatever is after the summation would be the value that you would get.
So that's the final equation here. And let's implement this using code, and I would like everyone to open Google Colab so that we can code linear regression. Wait.
This.
Hmm.
Don't do everything.
Okay.
Because everything else we can do it later.
Okay. So you just want me to import the for now.
Are you guys ready to go along with the code? Yeah.
Yeah. You can just go to Google Colab and start a new notebook, and we'll be doing the code. Is it okay if I copy paste? Or
Yeah.
do I need to code?
Okay.
Okay. So for now, we'll import NumPy. I'll type. So here we are importing NumPy for calculations and pandas. So we are using matplotlib for the plotting the scatter stuff like the graphs.
Good.
So you can just type along with me so that you can follow along with me. The data sets. Now for the data set, we are going to take the California housing data set so that
Is this visible?
now we are going to import that specific thing. So this is the data set we are going to use. Now we will be loading the California housing data set using scikit-learn.
What is the data type and stuff?
Yeah, I've actually used different cells for all those.
Oh.
Yeah. Okay. Okay. Do you know how to copy? Okay. Don't think it is no.
Join. Okay, it does not check. Oh, it is showing. Oh, yeah, so same thing, you can do control A, control C.
Yeah,
Yeah, okay.
yeah, got it.
Got it?
Yeah. So you're switching the line. Okay, got it. Yeah. So, let us know if you have any questions. We have all the technical officers around. If you get into any trouble, just let us know. Technical officers, please help them out. And here we are just importing the data set of California housing, and we are setting the target and printing the columns. So let's go ahead and run this cell and see the what's the result. So if you run this cell, you can see the table, which is it has many inputs like median income, house age, rooms, bedrooms, and so on. So target is nothing but the we are predicting the price, right? Using the medium income. So target is nothing but the price we are predicting of the house. So that's how this cell works. Now we just have to go to the next cell to get to the next part of the coding. Oh, no. I just want to scroll it.
Okay.
No, it's fine. Okay, I just have to switch. Okay. Now let's go ahead and yeah. Now let's create a, yeah. Do I need to scroll up? Let me know if you need time and we can go to the next cell.
If any of you are running into issues, just call us, right? We'll come and help you back.
They need time. It's
Yeah. Who? Oh, he can ask. We don't have a mic, sorry. Who has it down? Oh. Use autocomplete. Use autocomplete.
oh, okay. I was thinking to copy paste that. So here we are just converting it to the NumPy arrays so that we'll do the calculations later. For running.
Is everyone done with the first set? Yeah? Okay, you can scroll down.
So as we so for the X thing, we chose median income as X-axis and for target as Y-axis, which is the price. So now let's get started with the third cell. Here we are splitting the data. So for every data set, while training the model, we split the data into three parts. Like 60% goes to the training the model, 20% goes to validation, and the other 20 goes to testing that particular model. So we are just splitting the data over here, and then
The reason why you split the data is because, let's say we have all the data that we want, and how do we evaluate if our model is good or not, right? So the whole idea of machine learning is that we train a model, we test it on unseen data and see if it works well on that unseen data or not. If not, the model is not performing well and it's not generalizing across all types of values, right? So that's the reason why we are doing this train, test, and validation split. So how it works in real world is that you just have a train split and a validation split, because this is possible. And this is how it happens in competitions. Let's say you're working on a Kaggle competition. They'll give you a train data set. You have to split it into train and test, and they will have their own validation data set, which way they will use to test your model. So in order to show how it exactly works in a competition or in real world, that's the reason why we are splitting the entire data into three parts, which is train, test, and split.
all right. So now the next cell would be to calculate the mean and variance. So that and also we'll be using the same mean and variance for the all the three sets, like train, test, and validation. So let me know if you guys are done with this part of the cells.
So again, normalization is done to bring the values between a particular range. Let's say we have the prices in thousands, right? Like it'll be in thousands of dollars, whereas square feet will be like in a couple of hundreds. So the difference between the values is pretty large, right? So in order to bring both the uh, target and the data, which is the X feature and the Y features, into the same value range, let's say between 0 to 1 or -1 to 1, we look at normalization. And this is one way to do the normalization. There are other ways where you can get the maximum value that is present in the entire column and the minimum value, and then normalize the data using min-max separation. Just one.
You just have to go here, right? Yeah, go ahead.
Uh,
whenever, for example, this data set is very large, right? So we take only few data points. So after, if you want to run it again next time, it'll take the same data set, data points it took the last time, and it will repeat the same thing the next time you run the code cell. So that's how random is set to 42. So it's just a mathematical way of repeating the same data points we do for the next time.
So what to add to what you said, it's basically to enable you to produce like to make sure that the model is reproducible. The results are reproducible, right? So let's say if you don't assign that random state, you close this notebook and then you start to run it again. The results that you would observe would be totally different. So in order to just make sure that it is reproducible, we just assign that random.
Yeah.
You can take any number. There is no it's just been there. Everyone uses 42, so that's why we have it as 42. You can have it as 1,000 or a million, doesn't matter.
Okay, we'll go to the next cell.
So before that, is everyone done with that? Yeah. Oh, extemp is because we want to do train, test, and validation split, 3 different splits. First, we split the data into test and then temp. Then we take the temp and then split it into train and validation. That's all.
Shows that.
Yeah, because the train test split function, it returns exactly 4 values: the x of the train, a y of the x of the test, y of the train, y of the test. Now you're taking the test and again splitting it into 2 more parts. So at one time, test splits your data set into 2 parts.
Does that answer your question?
Yeah, but when I type it shows like it's not defined.
Oh, you're not getting it? Oh, you might have to run the import.
Statement, you need to import it.
Size.
Did you run this import station?
Just hit on run all and it'll run.
Anyone is facing issues? Is anyone facing issues with the code?
Cost. Can I answer it here?
Good to go? Yeah.
Roll up.
Is it good?
And from the beginning, he came just now, so you want to know who is good.
Oh, you can just look at your neighbors because everyone will get delayed by that. Sorry. Cool. All right, I think you can continue.
So this is the next cell we wrote code, again setting the random to 42. Since the data set is very large, I'm only selecting 200 data points so that we can see the visualization of the scatter plot. And let's plot the scatter, and I will show you the visual representation and how it looks. It just shows me that I have chosen 200 data points, and yeah, go ahead.
What is this?
Oh, it's just for reproducibility. So let's say tomorrow, if you want to run the same code and then want to get the same results, right? That is why you need to assign random state is equal to 42 or any number for that matter. Doesn't matter if it's 42 or 52 or 1,000 or 100, doesn't matter. It's just to make sure you can reproduce the same results tomorrow as well. So basically for reproducibility.
Is it okay if we share the code first?
Are you guys done with this set? If you didn't implement that percentage mat.lib inline in the first cell, just make sure you add it now, because if you don't add that, the plot will not show up.
So here I am plotting the graph. As you can see, I have named my X label, Y label, the title, and also a few colors. So if you hit run here, you'll see the graph of that particular data set. Scroll. Yeah. Just make sure to add that line, matplotlib inline, to see the graph.
Is anyone facing issues? These are all issues that you'll always face. It's good that you're observing them so that next time when you come up with the thing where you know what the issue is. Is everyone done with the plot? The last cell that is there, where we are plotting the graph. So if you're done with the plotting, and you can scroll up. You don't have the. No, just like another. We'll post it one. Like I listen to.
Is everyone good?
Oh, okay. Uh, any, um, This is where you are? Yes. Oh, shit. Good shit. Just a bit more, a bit more. We'll just speak up more. Yeah, good. Okay, thank you.
Yeah, so here I just gave you a few formulas, the line equation formula, MSE formula, and gradients formula. So let's go ahead with the next part of the code. Uh,
So now that we have all the initial steps which are required to get the data ready, we did complete data pre-processing where we kind of selected the only feature that we wanted, which was the mean, I think mean income was the feature, right? We selected all of that. We normalized the data, right, so that the label and the entire data is in a particular range. After we did that, we just selected 200 points in order to make sure that it is plottable for us and we can understand how the visualization is actually occurring pretty well, right? So with all of these kind of basic data pre-processing stuff done, what we will do next is we'll try to define functions that are related to the linear regression model. So the first function that you're seeing, which is the depth model, kind of explains what exactly, how do we represent the line equation, as simple as that. Next, in order to compute the loss between the actual value and the predicted value, we are implementing the MSE loss, which computes the whatever I just explained. So these two functions are depicting the two equations. Any question, doesn't matter if dumb or not dumb.
no question is done.
Yeah.
So the code for the text.
Oh, that's fine. This is just for your understanding. You can go with the code. We'll share the code file later by tomorrow so that you can refer to this later.
The thing is, I don't believe I got the code from the rest of what they have session.
Oh, it's, I think he can help you out with that. Is everyone done with this? Yeah. Good to go to the next equations. Some response would help, please. Are we good to go to the next equation or no? Yeah. Okay, cool. So now we know like what exactly is the equation for the linear regression model, what is the loss function, right? Next, what we want to do is compute the differential of the loss so that we can use it to compute the gradient descent and then reduce the loss during the training, right? This function is exactly doing that. It is trying to explain how do you take that one step, right? And that one step is nothing but the gradient of the loss function, and that is what we have implemented here. And once we do that, we want to get the values of the weights, the W and the B from the for the equation of the line, right? So that is why we are returning A and B over there. Is this visible enough, or do you want me to zoom in a little bit more?
Yeah.
Is this good enough? Okay. Is everyone done with this? No? Guys, yes or no?
Yes.
Yeah? Yeah? Okay, can go ahead. Did you all understand what's happening in the code, or do you want us to explain the code? Oh, okay. So you understood the model equation, the model function? Okay. MSA function? This one. Okay. So let me just go back to the slides. You remember this equation, right? So what we're doing, this is just implementing this in code, which is nothing but we are taking the y pred, which is the y hat, right? And then we are computing the mean of that by taking the difference of the actual minus the predict and to the power of it. Yeah. And then the step gradient function is basically implementing this equation, the second one in the back propagation, right? So what we are doing over here is we are taking all the x values, right? Passing it to the linear regression model, which is this, so that we get the y prediction as the output, right? We use that y prediction and then compute the error and then pass it through. And then compute the gradients of A and B over here, right? And then just get the A value and the B value over here. So with one step of gradient descent kind of defined, what we want to do is we want to compute it for, let's say, 100 steps, 1,000 steps, depending on whatever we want to do. We need to basically look at that, right? So that is where this gradient descent function comes in, where we are looking at the number of steps over here, which is 100, right? We take the initial values where, if you remember the blue line at the beginning, where it had a very low slope. We use something similar over here for A0 and B0, and then we compute the gradients by passing it through the model and then getting the values as output, and then get the predictions as output over here. So once we run this, let me know once you have implemented this so that we can go to the next one.
Let's go to the next code cell, which is calculating the values of MSE and also calculating the values of the gradients we just wrote the formulas for. So I'll just copy paste the code and you can just go ahead and type it in your laptops. So this is the next cell. As I said, we are going to calculate the parameters and also the MSE values. Here is the code for it. And when you run it, you can see the actual values calculated. So go ahead and type this and we'll be plotting the graph afterwards. Which one?
This is like the screen you can take it. Show that one.
Okay.
Does anyone have any doubts?
Any doubts in the plotting part or the previous part?
Is everyone done with this part of the code? So as you can see in the graph, I have only calculated it for 100 iterations. So as you can see, the gradient descent is gradually decreasing and eventually it became constant. So that's how gradient descent slowly comes down and maintains that low value. Let's go to the next code cell. So this is the final graph that we are going to
Oh, I'll just minimize this. You can keep.
yeah, go on. So if you run yeah.
And this graph is what Kaustav was talking about.
Yeah, he told me to stop. Mm, okay. We'll just show the best we can.
Just like that.
Okay. Something with the slides. Okay, so this is the end of the session, guys. Here we calculated the last scatter plot. If you have any questions, you can just go ahead and ask me now.
Any question? Anyone?
Regarding the whole session altogether.
Cool. We'll leave this code here if anyone is typing it or if anyone has any questions. The session's concluded right now, so you're free to go. There's food outside as well. If you're still typing it, we'll still leave the code over here, right? And any questions, you can reach out to any of us and then get.